we have to run OBS Studio. So today we're going to continue the histogram filter, and that is our introduction to then particle filters in the later part of the class. So the histogram filters, we designed a one-dimensional navigation domain where the robot can only move in a straight line, so it moves left or right. And like the Minerva robot project, we're measuring light. And we have a sensor model that indicates what happens when the robot is sensing something. So we're at location X in a given environment, and then if we're under a light, there is a certain probability that the true positive probability that we will detect the light, and one minus that we will not detect the light. And if our position is left or right of a light, then one minus the true positive ray. Let's put it the true negative ray. We will detect the light. Otherwise, we will find that we will detect empty cell. Then we can calculate the probability of the robot being in a cell, given cell. So the probability for our environment for the two locations here, we'll draw them in a second. And this is our environment. probability here, where all the bars are color. And also we still have 0.05 probability here on the first plot. Color green. Green I use for the robot here. So this is the 0.05 probability. Over here, C7, C8 have a probability of 0 because given the sensor model that we have, it's impossible to get a reading for light at this particular location. So now as the robot will drive around, or the next step that would happen would be that our robot moves. So we have to implement a motion model. Okay, the robot can move either right or left. Those are the only actions that it can execute. And if it reaches the end of the environment, then it will wrap around. So for example, if it's at T8 and it goes right, then it'll end up in T0, or vice versa for going left in C0. And then let's say the only command that I have is drive two slots. which will happen with 75% probability. Sometimes the robot will drive only one slot with 25% probability. So now you should try and implement the motion model. So for the motion model, what should be our input apart from like the current position of the robot and the environment? What else do we need to know? Cooling value of command to move forward. The robot only one function. Two, actually. Two commands. Two actions they can execute. It can drive either left or right. So to make that more generic and so that we can change it easily in the future, I can define the commands. So my command right is equal to 2, and command to go left is equal to -2. Then it matches the displacement that I target. Okay, and what should be the output of our motion model? What do we have to return? The treatment of our moving direction. Yes, how far we actually moved now, right? So if the command is, you can try and implement this yourself, or you should try and implement the motion model yourself. And I think this will probably do it, right? So first we define the distance as the direction that we want to move in. If the command says we want to go to the right, then it's greater than 0. Then we check if we match the motion probability, then we move 2 slots, otherwise we move 1 slot. And so this will either be D afterwards will either be -1 or -2 if we want to go left, or 1 or 2 if we want to go right, based on the probability. And then we calculate the target, which is the current position plus the displacement. And then we have to modulo the length of the environment so that we wrap around. Now, this one I'm actually not so sure, because what's the problem with this line of code here? The problem is I always forget which version of modulo the different programming languages implement. So for positives, this will definitely work, right? So if my position is 7 and I only have 5 slots, then 7 modulo 5 will be 2, and that's the correct index. If I wrap around 2 more to the starting from the left then. But -1 negative numbers can be tricky. So in this case, it actually works. For Python, it works. In Java, it will give you the early version of Java, at least I remember, they gave you a negative number, which meant that you would have to change this to x plus d plus the length of the environment, because then it's guaranteed to, assuming that d is less than the length of the environment, now you're guaranteed to have a positive number. But this should work just fine. So here's our motion model then. So let's have a look at our environment. And then, similar to the Kalman filter, there are sort of 2 algorithms in order to update our probabilities. First one is based on our sensor. So we detect light. Then we calculate a new distribution. And then I want to calculate the new distribution after the motion command. So try and implement and figure out how to implement the program so that you can update the distribution after the motion now. So here first we calculate the probability having the light, which will give us this figure. Will give us this image here. And now we move to the left. Move to the right. And let's define a variable corresponding to the position of the robot. And let's set up our So let's start with the position of the robot at the left edge. And I also want to have our current histogram. Yeah. And I didn't draw this before because it's sort of implicit, but initially every position is equally likely, right? So in this case, we have 9, so it's about 0.11. Sorry, yeah, 9 slots. So the probability is the same, uniform probability for each one of those. And then we can sense lighting. So now to upgrade the histogram, I need to multiply those together. And then afterwards, I need to normalize it because now my distribution is going to be the distribution of this and that. So we need to normalize it. Now in Python, I can actually write it. If you use NumPy arrays, you can write this a lot easier as just histogram is histogram multiplied by distribution because by default it does element-wise multiplication. And then it would be this divided by this will now do element-wise division, or should do.
This is the NumPy array version.
Yes, yeah. Otherwise, you would have to do it like you would need to do 2 loops through the environment then. However, that will be significantly slower than the NumPy version because if your state space is large, then NumPy uses vectorization in order to execute the multiplication in parallel, which is very easy to do in this case, right? Because you're going through 2 arrays and extracting elements that are corresponding to each other, then you just multiply them. So the Intel CPU has special instructions for doing that. If you program it like this, Python doesn't know about the fact that this is a very large array and that they're aligned and that the data types are uniform. In NumPy, this will run orders of magnitude faster. And then let's draw our environment, but I don't want to draw. Now I want to draw my histogram.
May I ask you, the array in Python is computed in memory as well?
It's what?
It's computed like a speech.
No. There's no array in Python, right?
Yeah.
There's only lists, and lists are not arrays because
It can do the memory.
yeah, I can change the size. I can also do that for arrays. Like if you look at the C++ array class, it allows you to concatenate arrays and things like that. So you can dynamically change the size of the array. In theory, linked lists were specifically good at being able to you would be able to add or delete elements with very few instructions. But nowadays, that really doesn't matter anymore. It's much more important. Arrays are a more efficient data structure for many use cases because they're much better in cache. So they sit consecutively in cache. However, Python arrays also, so Python actually uses array lists in order to give you fast access, but also the ability to make them larger and smaller to dynamically change their size. But the big difference or the big problem, it's not a problem. It's the way that the data structure was designed, and it's very useful. But the big thing why it cannot be consecutive elements in array is because in a list you can store anything. So one could be a floating point, the other thing could be a pointer to a class, next thing could be an integer, and the next thing could be a list of something, right? So that means that the thing that you can store in your array is really just a pointer to whatever data is sitting at that index. So you have like an extra indirection every time you access it. NumPy arrays, you specify what the data type is. So you say either explicitly or implicitly, if you say ones, then it will be integers. Or if you say ones float something, something, then there'll be floating point numbers. So those I can pack into memory consecutively. And I have instructions on the Intel CPU that will process them in parallel in a vectorization. But you cannot do that with standard Python list, even though internally it's stored as an array list, because you could have integer, 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 floating point, pointed to another list. Right? So then the processing doesn't make any sense.
So, the problem of the cache mix in the CPU.
Every CPU nowadays, your access time is sub-nanoseconds for cache memory and registers. So it's extremely fast.
and tens of nanoseconds for access to main memory. So every time you read something out of main memory, you have a 20 to 50 time penalty hit. And that's what is extremely expensive. But of course, if you run out of memory, then things are even worse, right? If you have to read data from the disk, then it's many milliseconds. Okay, so now we want to draw our new histogram distribution. So this is what we get after we sense lighting. So the most likely locations are C4 and C5. There's no way to distinguish between those two. And L0 is less likely because these two have the probability that it's under the light plus also the light from L2. Like C4, there's two ways that light can be detected in C4. One is that you detect L1 here. The other one is that this light from L2, because C4 is one off C5, right? They're neighbors. So there's also a probability that C4, even though it may miss this light, it may still detect the light from L2 here. And similarly for C5 and F4. So those two would have the maximum probability. This one has just the one from L0. It cannot get any other boost of the light. Okay, then we have our motion probabilities. And our motion model. So now let's draw and update our distribution, implement the code to draw and update the distribution, our histogram here, after we execute the movement.
We need to do is make a histogram of our motion.
Correct, the probability. So show you want to draw another picture like this. If I execute command to go to the right, then what happens to the red graph, the red bars? Because right now the robot is at location C0. If I tell it to go right, then 75% probability it'll end up in C2. Then what happens to the probability distribution?
C2 will do it, and the other position will decrease the peak probability.
No, not quite. Because I don't know that I'm in C2, in C0 right now, right? The only thing I know is this red distribution over the state space. So as far as the robot is concerned, where does the robot think it is now? Where, if you ask the robot, where are you? What would it return? What should it say?
It only can read the light.
Right now, we only can do, we started the robot up. So initially, the robot had no idea where it was. But the only thing it knows is that there's 9 cells in C0 to C8. So it doesn't know where it is. So then we said, okay, well, check your sensor. Okay. After we checked the sensors, the robot said, oh, I detect light. So it detected light. Also, it knows the map of the environment. So it knows where the light sources are. So then it updates its belief in what positions it's at. Before, these were all the same. Now we have this distribution. So where does the robot think it is? Yeah, one of those two, but it doesn't know which one. But right now it says my maximum probability is for cell C4 and C5. So most likely I'm in one of those two. And in fact, we can calculate what that value is in 0.23 or something like that. So 23% probability here, 23% probability there. This one here is 0.0. I wonder if we can. Yeah, let's draw the numbers as well. Draw the environment. Calculate the probability. Draw the distribution. So for plus 0.2 y 0.1 x I point 0.2f. And size 10. See what that looks like. Oh, X, not X. Um, is it plotting? Did it draw something else there? Huh, okay. I don't know why the drawing is so weird about it. Oh, because I didn't create a new figure. So yeah, and now this looks better after our distribution here. Now these ones deteriorated quite a bit, and most of our probabilities in those three cells here because we did sense that there was a light. So how should that picture change if I execute command right?
If you take, basically command run, the
Mhm.
robot will move it one or two steps, right?
Correct, yes.
The book, does the robot know where its truly location is?
No. All it knows is the location of the robot is given by its belief at being at certain location. So that means this probability distribution, the red one here, is what defines the position of the robot. the belief of the robot of where it is. Now, the one thing to realize in this particular position or in this particular graph already is that now we can easily represent multimodal distribution, right? Because this distribution has how many peaks? 3 peaks, right? Peaks as in local maximas. Then we would have 2 or 3, depending on how you want to count it. Doesn't really matter right now. The fact is more than one. So this kind of environment, we could not apply a Kalman filter to it. We will get a very poor result. Even if you use an extended Kalman filter, an unscented Kalman filter, none of those are going to be helpful in this world, in this environment. So now I execute the command. Now, if we're dealing with the Kalman filter, then this would be the predict step, right? Predict is when we move, update is when we get sensor data. So I have a command, and I want to take that code.
All the robot nodes is start from the C0 and
No, if it started from C0, then what would that picture here look like? If the robot started in location 0, then what should our distribution look like?
the 0 will be 1 and the rest of
Would all be 0. That's correct, yes. And then, of course, things can change, right? So here is this would be for an unknown start position. And this one would be so here, if the robot starts in 0, then our distribution would look like this, right? So now what will happen if I send slide?
C or
I just tell the robot with this distribution, I tell the robot that check your sensors, and then the robot will detect light, then what will happen?
You will consider only one light. Robot will assume there is only one light in.
No. The robot knows that there's 3 lights in the map. The robot knows the locations of the lights. In this case, nothing will change to the distribution. Why not?
Because the rate of the position probability multiplied by the light distribution probability will all come over zero.
Correct, yes. It's now completely sure that it's at C0, right? So it detects light. Even if it detects no light, which would be the wrong position here, right? It's so sure that it's at this location here that all of those are 0, so it will stay the same, nothing will change. Right? Now, that's because when we do the update step, what happens to our threat, to our uncertainty? When you think back to Kalman filters, when we did the update step, then what happened to the variance of our Gaussian? My current Gaussian, right? That's where I think where I am. Now I get a light sensor, and this is my sensor model here. This is my state. Then what will be my new estimate?
You will take the end into Gaussian distribution.
Yes, it'll take the end of those 2 Gaussian distributions. So the position is going to be somewhere between those 2, right? Weighted based on the variance of those 2 Gaussians. So if I'm very sure about my position, then the sensor is not going to, I don't trust my sensors very much. I'm not going to move very far. If I trust the sensor very much and not so much my position, then I'm going to move much further towards the sensor reading. If both of them are the same, then where it's going to be. If this variance is the same as this variance, then it will be in the middle, right? Halfway between those 2. So this is going to be my mean. And what happens to my estimated variance? Were you guys all asleep in class? I went through exactly this. Yeah.
The variance of the new Gaussian distribution.
Yeah, correct.
And remember, it will be decreased, but decreased.
Correct, yes. So the variance is still going to decrease, which means this peak here is going to be
higher.
So I end up with something like this, right? So every time we do an update step from the sensor, our uncertainty should reduce, right? Every time I make a movement, what happens to my uncertainty?
Increase.
It increases, so it's going to flatten out. So the same thing is true in this scenario, except I already have no uncertainty. So there's nothing that I can do in order to reduce the spread of this distribution. It's already 1 and everything else is 0. So nothing I can do there in order to make it more narrow. There's no uncertainty in this case here. You can also start this out with a so this is what happens if you are in a domain where your location at the beginning you're sure you're in location 0. So we can also do assume that the robot starts in location 0 or 1, right? And now a graphic would look like this. So now there's a 50% chance or 75% chance that we're in location 0 and 25% chance that we're in location 1. Now what happens when I sense the light? What does the robot think now? Now it switched, right? Before it was more sure. It thought it's more likely that I'm in C0. So my prior belief was C0, 0.75, C1, 0.25, everybody else 0. But now I detected light. So now, using the likelihood of my sensor, which is 70, if I'm under light, there's a 70% chance I actually detect light. There's only so if I'm in this location here, this one would correspond with 70% probability. This one, there's only a 15% chance that I detect light if I'm in C0. So that means that the posterior now is 0.4 for C0, 0.61 for C1. So my most likely location now has swapped. Now I think I'm in C1. Now let's finally drive the robot around, which is what I wanted to do the whole class. So now we have to calculate that. For all the slots, I need to calculate the distribution now. So for each cell, there is two ways, or each current element in my distribution will contribute to two other cells. One of them will be weighted with 0.75 because 75% of the time I will drive two spots. And one of them is going to be weighted 0.25 because with 25% probability I only drive one slot. So now I just need to go through my array and then add them all up. So in my history, the current value is H. And now I just have to make sure that I get the distances right, like the displacement, right? So this H now will be histogram 2 of I plus D times 2 modulo the length of the histogram and then plus. So in this case, I moved two slots, right? So this should be 0.75 or motion robot 2, motion prop 1, motion prop 2. And then one step, we move with probability 1. Then we convert it into a probability distribution again by normalizing it to 1. And then I can return this. And the command was from right. Mhm. We turn histogram 2 here, not. Continue. Income. Okay, so now it looks like this. We move, and for the different positions that we have, we move one slot or two slots to the right. And if we started here or here, so if I start here, that was the most likely one, then I would end up there. Or I will end up here with 25% probability from this location. From here to there, I will have 25% probability of my previous. But that was already reduced. That was 39% probability. So now this location here is sort of almost the one, almost the same as this one here, because there's a high chance, two possibilities. C2. Either I start in C1 and I only end up going one step, or I start at C0 and I end up going two steps. Right? So that's why this one here sort of has two components. If I'm in C3, then I must have started in C1, not in C0. So now you can see our distribution spreads out again, the different contributing factors. What will happen if I do this continuously now? If I just keep driving to the right?
It will be the flat distribution of.
Yeah, eventually it'll basically be 11% everywhere. So now we'll do another sensing. So let's say I sense no light in this case. And actually, let me split that up in two. So update the sensor with the environment and the reading set. And I want to map it, make it symmetrical to motion predict. Home history. Last step to normalize it. And so I have to start again from the top. Now this is our distribution. Then what did I say? We wanted to update sensor that it's empty and histogram and this is the environment. And we want to plot that. So this will happen now after we sense that we got an empty location. And that would be following this figure here. So now this one, the 0.10 here has been decreased dramatically because if we're in C1, then we shouldn't detect. There's a slim chance, only 30% chance that we'll detect no light. So those two now are, those two locations are a possibility. Then we can go to the right again. And now let's say I detect some light. Okay, and now you can see now the robot thinks much more. So given the fact that most certainly we started in C0, then then we detected no light. No, then we detected light. Then we drove one command to the right. Should have gotten us 2 steps. Then we detected no light, and then we did another command to move to the right. Now we detected light. Then the result of this is that our most likely location now is on C4. Now, because the spread I used is pretty high, what would it take to actually be more than 90% sure that we're in any particular cell? How would we be able to achieve that? Well, the only way I can reduce my uncertainty is
moving back and forward
no,
in the sense that near,
no, moving doesn't help me.
of
Apart from the fact that if I do it multiple times, then you could say, oh, with the central limit theorem, your mean should be 0, right? That would be true, but that doesn't really help you because even if you now know that you're back to where you started, there's a good chance that you're back where you started, you still don't know where you started, right? So that doesn't really help you. No, the only way to reduce your uncertainty is to do sensing, right? So if I now check 5 times and I end up with 5 times, I read sensor light, then the probability will go up correspondingly. So we can do that. And then look at the output. I think this domain, yeah, nothing much will change because this one is already almost 0. So there's no way that yeah, it's just this 0.01 will be further reduced. So what's more, so if I do that, it doesn't, if I sense light, it gets not more information to distinguish between those two, except this 0.01, this small part now will be distributed between those two. It's more interesting if, how do I, it's more interesting if I sense empty here. Let me just print what. So this is millions here, 10 to the minus 6. But if I now sense, so even though there's only a tiny fraction, if I now sense no light, now all of a sudden this part here will be much more likely. And this is the one that would be winning, so I could push this up higher. But there's also this little part here was also still a possibility, and this now is also being increased by the sensor reading. But now I took 50 times sensor reading, I think. Yeah, 50 times. So, and assuming that the sensor readings are statistically independent, so if one of them makes a mistake, then the next one doesn't make a mistake, or makes a mistake with the same probability, then this is what must occur. Now, that's one thing that is usually not true, right? If your vision system is in this position and you cannot detect the ball, then if the ball stays in the same position and if your robot stays in the same position, there's a much higher chance you won't detect the ball in the next frame either, right? So there is some statistical dependence between the sensor readings. However, to model that would be statistically not possible. You'd have to collect all the data in order to be able to model this dependency. So we make the assumption that it is statistically independent.
Why the sensor reading will independently in the sensor reading of
if you implement your vision system and you detect blue, right? Then under this lighting condition, your blue looks purple. So you don't detect the ball. If the lighting doesn't change, if your position of the robot doesn't change, then it's still going to look purple in the next frame. So that means there's a very strong correlation between the sensor reading at time t and the sensor reading at time t+1. Right? So that means they're statistically not independent. Okay. Because it's basically you're looking at the same scene. Or with an ultrasound sensors have problems with bounce off. So if you're bouncing ultrasound off the wall here, you bounce off there, go to the corner, and then come back. So you measure a time that is too long, you estimate that the wall is too far away. Because my robot is sort of an oblique angle to the wall. So if I send sound waves, they're going to go here and then bounce off. That's a very common error in ultrasound sensors. If that happens at time t and I don't move my robot and the wall doesn't move, then at t+1, much higher chance of people. Right? Whereas the overall probability will be just anywhere in the environment, then it depends on like how many oblique walls there are while you're driving. So that's why if you sense and then you drive, then you sort of have a new possibility, right? New location, new environment. So if I cannot detect the ball from this location, but I walk to this location, then often I either can or cannot detect the ball, but it's much more independent of what I previously. So that's why you want your robot to move around. Like with our soccer playing robot, that's our last resort strategy. If we cannot see the ball and we don't know where the goal is, then sitting there and not doing anything is also not useful. So then the robot will start walking around slowly.
Then working.
Right, the ball, yes.
And it can interfere the competitor.
Well, yeah, or kick the ball into your own goal, which sort of hit or miss. But it's better than not doing anything, I think, for sure. So as a strategy, I think it's a good strategy too. Okay, so now we have the histogram filter, because this is a histogram of the environment here with our probability distribution discretized over the environment. And this would actually allow us to localize our robot if your sensor is good enough and we're driving around. If I drive around multiple times, then the robot will actually eventually will localize to a particular position, because if I keep going around here, it's going to latch on to this pattern of one light, two lights. And so I can either go up and down, or up and wrap around, keep going right. That doesn't matter. No, but the more, so even if I start out with a unknown initial location, where I think everything here is 11%, 1/9 chance of being the correct cell that I'm currently in, eventually it's going to converge. Like in this scenario here, now if you ask the rover, where are you? Most likely it's in C3. So then you can do your path planning. You would say, oh, I think I'm in C3, so what command should I execute next? So that would mean that the histogram filter is able to localize the robot, depending on the environment, of course. If there's no light, then there's nothing to sense, right? In that case, the robot will not be able to localize, because there's no features. It's like driving through a fog. So there's no way that it can possibly improve its or reduce its uncertainty about its current location. But with a reasonable environment, the robot will be able to do that. Right? It will localize. Which is the most difficult part of the SLAM problem. You can sort of think about trying to localize, and now I keep driving here, now I detect the light there, then I can update my position, my environment, then I can just put a light there. And so the localization is the harder part of SLAM, usually. The mapping part is comparatively easy. So that would mean that we're done with our SLAM sort of problem. And in a sense, we are, except what is the problem with this histogram filter?
I think at least we need to localize one time in your robot.
No, actually I don't. If I have a reasonable environment, eventually it will localize. If there is a way to localize, the histogram filter will find it. It's also sort of optimal. It's a Bayesian filter, right? You can think of this red here as our prior. We have the likelihoods from the sensor or the motion, and from there we calculate our posterior. Now our posterior for the next step becomes our prior. We apply the next likelihood, calculate the next posterior. So it's a Bayesian filter. It's a recursive filter. I don't need to keep track of the whole history of commands and sensor readings that I have, right? The only thing I need to keep track of is this current probability distribution. So that's nice, but that's also the problem. That's why you really cannot use the histogram filter in a practical SLAM domain, in the navigation domain. Computationally, it is not very efficient. Why?
To accumulate all the data.
No, I don't need data from the past. I only need data about the current time slot. But what do I need to know?
The light distribution.
Yeah, the sensor model, yes. The problem is we need to discretize this probability distribution here, right? Which means that if my environment is large, then this will be a very big array here, right? If I have 10 cells or 100 cells, this is not a problem. If I have 10 million cells, then this would be a problem. So this wouldn't work on warehouse size, for example. 100 meters by 100 meters, you want to break it down into 10 centimeter squares. It's computationally, it's going to require a lot of memory. Right? More importantly, computationally, it is not very efficient because
the probability we need to count in the location we need to count in far more than all the probability space.
Right. The interesting part in this distribution here is all this area here, right? But if I have 1 million cells, my histogram filter is going to have to iterate over the 1 million cell, right? Now, most of those are going to have a value that is very close to 0. The prior is going to be very small. So that means that I'm doing a lot of extra work where I know that the final result is going to be something very close to 0 multiplied by a number that is less than 1 is going to still be something very close to 0. So it's not going to have any impact. So computationally, we're sort of losing focus. What we really would like to do is focus in on this area here, right? And saying, okay, here, okay, that makes sense to calculate it because I need to figure out which one of those is the most likely one. And somehow ignore this large stretch of state space that is not very likely that break. So that's the, and this is what usually happens in a SLAM domain. If your robot starts driving around, collect sensor readings, our soccer robots start to walk around, then see the field lines, it can see the goalpost, eventually it's going to be localized. So there may be usually, hopefully, just one location. Sometimes there's two, like sometimes the robot, if you see a field line or a circle, right, part of the field, the center circle in the soccer match, you don't really know which side of the field you're in, right side or left side. So then there's sort of two peaks. But there's only those two areas that really we're interested in. All the other ones, their probability is so close to zero that they don't really matter. And we want to be able to control the sort of amount of memory. If I have a very large environment, I don't want to have to discretize every cell. And the algorithm that does that is pretty much the same, very similar computation, except we're using a very clever trick, very elegant algorithm in order to represent this distribution. And that's a particle filter algorithm. And that's the algorithm that is used in in the vast majority of modern SLAM algorithms. Particle filters are extremely popular. It's like A* for search. It's a very powerful, very elegant algorithm. And we're going to look at it next. Oh, and the last problem that we haven't histogram filters, of course, is this idea of discretization. Do I need a 10 centimeter by 10 centimeter box, or do I need can I do a 1 meter by 1 meter box, right? So the size of the discretization is also important. And it's not apparent what that should be usually.
So the discretization area is too small. The only side effect is the computationally comfortable.
Yeah, computationally there'll be a big overhead.
So the only.
But of course, the bigger your cell is, the less precise your localization is too. Like, I could just say, I want to localize my robot. I use histogram filter in this room, right? If my cell size is 20 meters by 20 meters, then of course my histogram filter is computationally very fast, very efficient, because it's just going to calculate one for the robot being in this cell And that's the only cell there is, because the whole room is smaller than 20 meters by 20 meters. So it's non-trivial to find the right value for your cell decomposition, your domain discretization. Like in so many other domains, discretization is always a problem. You clearly sort of, you don't want it smaller than the robot itself, usually, right? So if your robot is like this size, then the minimum cell size you would consider is probably the size of the robot itself. That's not always true, but that's a good rule of thumb. And then it sort of depends on your movements and motions that the robot can do. Now, the other problem with this cell discretization is it's not, strictly speaking, part of the histogram filter. Like in theory, you could implement it so that you have a variable size for the histogram. Not every cell must be the same size. It's not necessary that every cell is the same size. That's sort of a simple extension to do to make to the histogram filter. That is actually often quite useful in domain. If you develop you want the robot to drive around this room here, then this area here, you can have 34 cell decomposition. Because realistically, even if I take 4 cells, 4 of the squares, right, or 9 of them, then anywhere where the robot is here, if I wanted to navigate, it can drive around and eventually it will get a sensor reading, right? So I can have a very large cell decomposition there. But if I want the robot to navigate through here, then I need to be much better localized. So this idea that you have one size cell decomposition is problematic in navigation. It's computationally very expensive, and it also, because you need to represent all the cells, you need to update all the cells' probabilities. And depending on what the navigation task is, your cell decomposition may be better to represent it in different sizes, depending on how important the exact location is. Those are sort of issues that come up in practical SLAM. Particle filter also manages to solve that very nicely. So not only is it computationally more efficient because we can focus in on the part of the state space that is most likely to contain our robot, but it also allows us to sort of have a variable discretization. Now, particle filters don't actually do any discretization. We'll see how they work in a second. So they're similar to Kalman filters. You want to be able to track multiple hypotheses. And here I've developed a small model of a differential drive robot, a class to represent that. So it's a robot that has a location, a position, XY coordinate, and a theta, an orientation. Now, if the robot drives forward, then we have a motion model which has a standard deviation, some noise that we can add into the motion of the robot. So this is a more realistic robot model than what we discussed before. So it actually has an orientation. It's 2.5D, and it can do more than just, it can turn left, right, and go forward and backwards. So it can do more than just go along a straight line. And also, when you're dealing with angles, then it's always a good idea to normalize them, because otherwise you can end up with bad results, in particular once you need to calculate differences of angles, like in order to get the direction to a target or something like that. So here we have a motion model forward, which drives the robot distance forward. We add some Gaussian noise to it, to the distance that we travel, and a turn, which is also maybe distorted by Gaussian noise. So then here I send some commands to the robot. And this is really to look at to develop the motion model and to develop a intuition for the motion model. So far, when we dealt with the motions of the robot, we just made the assumption using the central limit theorem that our resulting distribution is going to be normally distributed as well. But now here, I actually run an experiment. So I start the robot at location 0, 1 and 0 degrees. And then I drive it forward by 1 meter. And then, so this is the distance and then the turn. So I drive it forward by 1 meter, 3, 4 times. Then I turn left 90 degrees. Then I go forward 1.25 meters. Then I turn left. Then I go forward 1 meter, 1 meter, 1 meter. And then I run that 1,000 times, and I simply record the positions that the robot goes through. And then this is the output that we actually get. Now what do you see?
Multiple things in the distribution space. And
Not really. There are multiple peaks now. The red circle, those are just because I show 1, 2, 3, 4, 5, 6, 7, 8 commands. So if there's no noise, then the robot would have gone here, 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 here. So those peaks are the position of the robot at different times. So at T0, the robot is here, center, then we drive to the right one time, right? And then I drive to the right again. And then I send another command to go to the right. Here I say turn left, so I go up here, go up 1.25 meters, go up here, 1.25 meters. Then I say turn left again, and then I keep driving this way. So up here, for the last position, it's a little bit hard to see, but for the last position, after the sequence of commands, what does the probability distribution look like? Yeah, that one looks pretty much like a Gaussian with no correlation between X and Y sort of circle. But what about this part here?
There is no correlation.
Yeah, this is not even a Gaussian, right? Because it has this banana shape. Right? It looks like a banana here. So that means that if you want to implement a navigation algorithm, a SLAM system, that distinction, that difference, is useful to know and maybe important to your system. So in the broadest sense, you can just say, okay, my motion is this motion plus some Gaussian noise added to it. But if you actually look at it in detail and investigate the source of the noise in your system, often you can come up with much better approximation. So sure, after a lot of commands, you end up with Gaussian distribution. Right? But usually, you don't have so many commands before you do another sensing circuit, right? So then, to model it in using this banana shape may be important to your algorithm. It depends a little bit on your domain and how powerful your sensors are. Because your motion is going to spread out the uncertainty, but this uncertainty is very different from a Gaussian uncertainty here. So if you model that, then you have a better idea of where the robot really is. However, if you drive and you have lots of sensor feedback all the time, then you may not care about the motion model. Right? Because you can always use your sensors to decrease the uncertainty in your system. So that depends. But this kind of navigation is quite difficult. It's important to understand most models, even for humans, right? So when people are stranded in the desert, the plane crashes in the desert, and then they're trying to walk to the nearest city, or they don't have water and they want to find the source of water. So they know this is the direction to to the lake or to the ocean or to the city, then what usually happens?
They don't have compass.
Yeah, they don't have a compass. Yes.
Well, the worst case, they will walk around in a circle.
Yeah. And it's not just, it is the worst case, but it's also the common case. There's been many events where people walked around trying to get out of a desert and actually ended up walking around in a circle or a circular loop because
You know, speak likely not equal. No,
the feet are not exactly the same length, that's right. And also you have a dominant leg. Like usually for people, for me, my right leg is stronger than my left leg. So in the desert, if everything is flat, right, and you cannot see any landmarks, then very likely after several hours you start walking around, and for a couple of days you come back to not exactly the same place that you left, but pretty close. And people have died because of that. So you would need to have some kind of external reference in order to help you with your navigation. Humans are not very good at reckoning over long distance. Not like homing pigeons. Homing pigeons are very good at that. So then having understanding your motion model is important if you're stranded in the desert without any visual feedback. Similarly for your robot, if it's stranded in the desert with not much sensor feedback, then it's important to be able to model the motion accurately. If you have lots of sensor feedback, then of course you can use that in order to reduce the uncertainty in the position of your robot. Then your motion model is not so important. In fact, if you have a rich domain, or if you use a LiDAR scanner, often you don't even need a motion model because the LiDAR scanner gives you all the data that you need at any time. Okay, good. So here we have a sensor model. Now, sensor model we've also modeled so far as applying Gaussian noise. But in reality, they're often the sensor model is different. So for ultrasound sensor, for example, so here we just measure doors. So we check the distance to the door and we check whether it coincides or doesn't coincide with the measurements that we got from the sensor. But even the sensor model itself is usually not like this. With our vision system for detecting the ball, for example, yes, there is some Gaussian noise. So if you look at the ball, the box is going to jump around the location of the center of the ball. Now, that Gaussian noise for our soccer robots is actually not a problem because the robot sees the ball and then it's a little bit to the left. So he walks this way. Then next time he sees the ball is a little bit to the right. So then it'll go this way. So just like keep walking up, the robot is sort of calculating the average of the positions that it got from the ball detector. Right? So that Gaussian noise in tracking is, that one is sort of averaged out by the mechanics of the robot. But that's not the one that is very bad for performance. What makes what causes huge problems for our surface playing robot would be, we see the ball there, and then the robot walks a little bit, now the lighting changes, it doesn't see the ball anymore. But it's really trying hard to find the ball. So all of a sudden the ball is not there anymore, but over there. And this happens a lot with field lines, because the ball is white and the field lines are white. And if you look at the field line with the right angle, then it looks like a ball to the robot. So then if it can not detect the ball well due to lighting in certain parts of the field, then it jumps like all over the field, 5 meters away, no Gaussian distribution there. So then you need to model that as well properly if you want your particle filter to work properly. Or, so instead, it may look like this for our sensor model, right? Or if you have ultrasound sensor, the response, if it's too close, if the object is too close to the sensor, right? That's true for LiDAR too, then you won't be able to detect. So if it's very close to the robot, you don't get detection, then you sort of get some good sensor response, and then it deteriorates, and then you have a peak at the very end where the echoes are coming back. So this is sort of what the sensor model would look like for an ultrasound sensor. Not really Gaussian at all. Usually drops off. So now, particle filters the idea is that we start our robot at a So in order to be able to do localization, in order to implement the SLAM algorithm, the algorithm must be able to represent the uncertainty about the location of the robot, or if you're tracking something, the object that you're tracking. It's a similar idea in this case. Now histogram filters. Discretize the domain and calculate a probability for each cell, which is computationally not very efficient. Particle filters use what's called particles. And a particle is one possible location of the robot. And its associated probability. So they're like sample traces or sample locations in our environment. So how does that work? Let's see, we have a domain with 3 doors. And the sensor where the robot says, okay, I can detect the door. The sensor model is based on the distance between the robot and the door. And the robot is limited to a one-dimensional domain. So it can only move right or left. It cannot get closer or further away from the door. Now, a histogram filter with the lights, we would develop different cells. We would discretize this domain. With the particle filter, we basically take out different locations in that domain and associate a probability with it. So my robot starts at location 0, 0 and 90 degrees angle to the right. And uncertainties for distance and turns in the motion. So this will be my motion model. Then I put the robot at that location and I give it a command to go to the right 30 times. So here, I send these commands 30 times 0.25 units to the right. And then I simply drive the robot to see what would happen. So it simply executes move forward commands. So I'm doing this part here, but instead of driving 1 meter, I only drive 25 centimeters, and I do it 30 times in a row. So at the end of this, I should be at position 7.5 meters. I should have moved every time I move 25 centimeters, then the mean of my movements is 25 centimeters because they're Gaussian. So eventually I'll be at 7.5 meters. So here I generate all these, I keep track of where I should be now, the possible locations. And then I sort them based on the x coordinate just so that I can plot them. And I change the y coordinate to draw them at 6 in the figure. So then I detect a door. I have some doors in my environment and the maximum sensor range. And I then calculate for each possible location, how well does it match my current sensor reading, which is measuring the existence of a door. So I detected a door. And then I can plot what just happened. So my start location at 0, 0, and then the outline, so the wall from -10 to 10 at height 8, and the doors, 3 doors that I plot in there, and then I plot the positions. So these are the positions, and the size of them is given by how well it corresponds to the location of the door. So that's my posterior probability there, a measure of the posterior probability. And the line down here would be the non-normalized probability distribution for this location here. So I start over here, then try and move there, and then depending on how much my motion was distorted by noise, these are the positions that I ended up with. And the darker circles are the ones that correspond closer to the sensor reading then. And this is at the heart of the particle filter algorithm. So now instead of discretizing it, I basically keep track of possible locations for the robot. And I need to keep track of the possible locations, but also of the posterior probability of those positions. This is the first part of the particle filter algorithm.
now what we can do is instead of calculating for every cell, breaking like the histogram filter, breaking it down into cells, and then iterating over all the cells, what I could do is I just say I start out at my current location and I generate these particles, and then I just keep running through that. And then that would be the possible locations that the robot could be in. I simply keep track of these particles then as my robot drives around. Right? That's the first part of the particle filter algorithm. Now I can control sort of my runtime. If I want to be very precise, I can generate 1,000 particles. If I don't have so much time, I can calculate only 10. Right? So it's just a Monte Carlo. So that's why the modern algorithms for SLAM are all Monte Carlo based localization methods. That's the first part of it. Now, given that I do this to the particle, what would be my most likely position there? The mean of your not the mean, no. I mean, the mean, the command that I sent sort of changed the position of the particles at the end, yes. But let's say if I have an unknown sequence of commands, and I end up with this picture here, right? Where I now have, if I just drive it, if I ignore the sensor reading, right, then I would end up with exactly this picture. Right? Here I don't have any sensor reading. So each one of the dots has the same probability. Right? Now, given this kind of representation, what would determine the position of my robot? How would I determine the position of the robot? And ignore the top part here, if we just look at this part there. Finding the mean position of the particle. The mean position of the particles, but if I run this, eventually I also end up with positions that are very far off here. So if I just calculate the mean of this, that only works if I have a Gaussian distribution. In this case, we may not actually have that. I could do this in any way that I want. But the way that I would actually be able to determine what my most likely position is would be the density of the particles that I have. The more particles that I have in, let's say, a small neighborhood around myself, the more likely it is that this is the correct location. Because I ran 1,000 trials, and a lot of them, 900 of the particles ended up in a position that is close to this location here. Right? So in that case, this is the most likely expected location that I'm at.
So it's the density of the particles that matter in this case. Not the mean, because I may end up with outliers that will greatly distort my location there, if I calculate the mean. It's not if you're dealing with a Gaussian distribution, but if I can do the same thing with the sensor. If I have the robot sitting here and I have it detects the ball over there. And now I take 100 images and 80% of the images, the ball is at this location, plus or minus a little shift, right? And 20%, the ball is over there, plus or minus a small shift. Then, if I calculate the mean, I end up with some location in the center there, which is no good because there's no ball there, guaranteed. So instead, I would want to check how often do I get a position that is close to this location and how often do I get one that's far over there. So what matters is the density of the particles in a particular area. And I want the location that I want to use, the position that I think where my robot is located at, would be the location with the highest density. And this is the same thing that we would have here. So I just run these particles. So then for these locations here, we sort of would get a fairly normally distributed, because we're only moving in one line and I keep adding 30 plus or minus some standard deviation. So I added 30 times distribution here. But really what I'm interested in is the density of the particle. So then, that's okay. That now means we can use particles in order to represent what happens through the motion of our robot. But now, what do we do with sensing? Other sensing effects. So now I have some particles. They are different locations. And now I take a sensor reading, light. The light is above. So now what should happen is that some of the particles should become less important because they detect, now right now I should detect no light, but I actually detect light now. And the ones that actually are under a location of light or in front of the door, those ones should get more important, right? We would put more emphasis on those. We would think it's more likely that those are the correct particles. And that's it. Then I can add the weight. So you can see the different weights here. The particles that are in front of the door get an increased weight. The ones that are further away from the door get a reduced, their weight is reduced. So then what do we want to do? Now the problem, that part is the first part of the particle algorithm. So we start with different locations and then we spread them out, we move them with the motion model, and we can calculate sort of how well they correspond to the sensor reading. And now the particle filter does a, so that initially you may think that that would be sufficient, right? Because now I have particles, now I have a prior probability, right? Because these ones here are more likely. Now I drive again. Then their probability may decrease, right? I do another motion command, then I get some more sensor command. So each one of the particles has a weight associated with it, which basically tells it its prior distribution, prior probability. Now, what's the problem with that? Not too bad, because I mean, the efficiency initially will be okay, right? Because I can control how many particles I want to use here. If I want 10 or 100. And the size of the particles will be independent of the size of the domain. I can use 100 particles in order to model several kilometers of wall there. Whereas if it discretize, if my environment becomes bigger, then I need to represent more scale. So that's nice about the particle filter. It doesn't scale up with the size of the domain. It scales up with the uncertainty in the motion model, really. However, let's think about what would happen, like in our light bulb domain, or this is basically the same thing, only with doors. What would happen is that I have these particles, and now these ones here all have very small probability, right? But then in the next step, I have to move them. So now they have a small probability, I move them, I still end up with a small probability, even smaller, right? Because when I move them, the uncertainty increases. And eventually, what will happen is that there's a couple of particles that have a high probability, and all the other ones are going to be, they're all going to have a very small probability. So the particles are going to die out over time. Because if I, let's say I have this particle here, now they have a reasonably good probability. Same as these, same as this one here. Slightly less, but almost good. Now I go one door width to the right, and I detect a door. Then all of these particles, these ones here are all zero. Then if I go to the right, I detect the door, they're still going to be very small, because they are already very small, so they can only get worse. This one here is going to the right, it's also going to decrease. This one here is going to the right, but there's no door there, so this one is going to decrease. So the only particles that will still have a reasonably high probability are the ones that correspond to this door here, which is what we want, right? Because now we localize, now we know that we're at this location here. And before we were at this location. But then it's silly to keep track of all of these other particles. So the particle filter does a very clever thing. It resamples the particle. So instead of always using this set of particles, after we update our sensor, we sort the particles based on their likelihood, based on this weight here. And then we draw from this distribution so that the particles that have high probability, that have a high weight, are more likely to be drawn. And then I just generate 100 new particles. So that means the particle filter automatically will always focus on the areas where there is a high likelihood. It's going to focus on the interesting areas here and here. And there will be almost no particles in here and in there. So this is the really clever part. Technically, that's called importance sampling, because we're constantly changing the makeup of our particles to focus on the important regions, on the ones that have a high likelihood of actually being correct. So this is it here. This is the resample step. So we calculate a new set of particles, a new set of positions. I sum up the weights, cumulative sum of the weights, which gives me a probability that ranges from 0 to 1. Then I draw a random number, and then I simply go through and check which one that particle belongs to or is assigned to based on the weight. And then I add that particle to the new particle array. So here, after this set, we have multiple copies of existing particles. And then I'll explain the next figure next Monday. Basically, here we're resampling it then, and we get the green particles. And this will be the new set of particles that we'll continue processing. We go through multiple iterations of the algorithm. Good. And that's it for today. Please fill out the form.
没有法维护那个门槛，尤其那种展览馆，对啊，盖得那么漂亮，哇塞哇塞，
做他们的那个防御上限，造成了我们防御上，
蛮短，蛮短。
新一区都有防御上限，才会有
它应该有，哎，没有，60块，60块，如果还单人就他赚不了钱，对，
新一区有是一个
有
好像是
有200，可是上面的300，
因为它文化有很多把它防御上限就180。Yeah.
And I also recorded on here, so
哦，你就知道。
I stopped it.